are you able to see my mouse cursor on the screen?
Yes, yes.
Okay, great.
You are moving it, right?
Yes, great.
Yes, sure. Very nice first slide.
Yeah, this movie was made by space.com from a press release we had about a year ago. That I'll
Nice.
show some of the images from.
Very good.
Mhm.
I'm going to accept people. Let's wait a few minutes and then we start. Well, I think we can start. So good afternoon, everyone, and welcome to our PAHs seminars. Today it's my pleasure to introduce Dr. Rebecca Levy. Rebecca earned her master and PhD in astronomy from the University of Maryland in 2021. From October 2021 and September 2024, she was the National Science Foundation Astronomy Astrophysics Postdoctoral Fellow at the Department of Astronomy at the University of Arizona, Tucson. Since September 2024, she has been a postdoctoral fellow at the Space Telescope Science Institute in Baltimore, where she is part of the Interstellar Medium Group. Her research focuses on the effects of stellar feedback in nearby galaxies using multi-wavelength observation of gas tracers. She combines data from ground space-based observatory, including JWST, ALMA, and Hubble. She has led several observational proposals at SPI, including program with Alman and Sophia, and has contributed as co-I to multiple projects with the JWST, BLA, HST, NOEMA, and other facilities. Her main research interests include the role of stellar feedback in shaping the interstellar medium and galaxy evolution, multi-phase gas kinematic and dynamics in nearby galaxies, young embedded star cluster in galaxy centers, multi-wavelength spectroscopic observation, and radius, millimeter, near-infrared optical integral field unit. Today, Rebecca will present her talk, JWST observation of M82, massive star cluster, and the base of the galactic wind. So thank you very much, Rebecca. The floor is yours.
Great. Thank you so much for that introduction and for the invitation to speak with you all today. I'm really excited to present some work that our collaboration has been doing with JWST observations of both M82, and I couldn't resist putting in another starburst galaxy, NGC 253. So before I dive in to all of the great results that we've learned from JWST, I am by no means the only person working on this. We have a large international team of more than 50 people who are part of this project and who are working on the data. The PI of this project is Alberto Bellato at the University of Maryland. And many of the papers that I'll be talking about today are being led by junior folks in our collaboration, which is wonderful. So sort of to motivate why we should care about these starburst galaxies and why it's worth studying them with JWST is really trying to answer the fundamental question of how has star formation changed over cosmic time. We've known for a long time that if you look at the cosmic star formation rate density, which is plotted here on the y-axis, as you go back in time, the rate of star formation around redshift of 2 or cosmic noon was much higher than it is in the present day universe at z of 0. And so one of the major questions is what is driving that evolution in the cosmic star formation rate? More recently, we know that it's not only the star formation rate that's changing over time, but the density of molecular gas has similarly changed over time, where this molecular gas is the raw fuel for star formation. And so it might, seem, trivial that, okay, you have more gas in the universe, gas is needed to form stars, and so that's why you have more stars. So is it just really as simple as more gas means more stars? It's not really that simple, unfortunately. So galaxies in the distant universe looked different than they do today. They were clumpier, they were more compact. They didn't necessarily have all of this beautiful spiral structure that we see in galaxies today. And the one implication of those clumpier, smaller, more compact galaxies is that the gas in those galaxies is more confined. So the cold gas that's in there can't really spread out. There's higher pressures that are confining the gas. And when gas is more confined by external pressure, it collapses more rapidly and to higher densities and with higher efficiency. And when you have higher efficiency of gas collapsing, you form not only more stars, but you form more stars in massive clusters. Again, because that gas is confined, it's more efficient at turning that gas that it has into these massive star clusters. And those star clusters that form with a higher star formation efficiency, because although there are more stars in those clusters, and so in principle, the feedback from those stars is stronger, again, the surrounding environment is so dense that the feedback isn't very efficient at actually getting rid of the rest of the gas from the molecular cloud. And so that means that, again, more of that gas will be turned into stars because it can't be expelled because of this denser environment in which these star clusters are found at earlier times. So this means that this high efficiency mode of star formation is different than we see in the current day universe because of these sort of environmental and morphological factors. And it doesn't appear to be just simply a scaled up version of present massive day star formation. There is something physically different happening to form these massive clusters and this heightened star formation rate at cosmic noon. These conditions were likely much more common at cosmic noon, as I've said, but they are rare today and only found in starburst galaxies. And so we can use these low redshift starburst galaxies to study the detailed physics of this mode of star formation, where we have things like physical resolution that we simply won't get at higher redshift, even with the next generation of facilities. And so with that sort of motivation, I want to introduce to you one of the key laboratories that people have been using as an analog for high redshift galaxies, and that's the galaxy M82, which is probably the archetypal starburst galaxy in the local universe. M82 is very nearby at a distance of only 3.6 megaparsecs. It's a barred disk galaxy that's seen edge on. So here in sort of the blue and yellow is the disk of M82. There is a bar buried down in there, but because it's edge on, it's really only visible with stellar kinematics. People sometimes forget that M82 is a small galaxy. It has a dynamical mass of something like 10 to the 10 solar masses and a dynamical radius of about 4 kiloparsecs. So it's quite small. It's not an L-star galaxy. And M82 is interacting with the M81 system. So if I zoom out this image that I'm showing here, this is actually the full image of the M81 group. So you have the main galaxy, M81 in the center, there's M82 up here, and there are some other dwarf galaxies around, in particular this one down here, which is fairly massive. And at first brush, it may not be completely obvious that these galaxies are interacting with one another. But if you look at what the neutral gas is doing, it's clear that these galaxies are tidally interacting. So this is an image of the H1 emission tracing cold neutral gas. And you can clearly see these bridges of material connecting these galaxies and having some weird morphology around M82. So this interaction with the M81 group is triggering a starburst in the center of M82. Or sorry, the interaction with the M81 group is triggering a starburst in the center of M82. And this means that this galaxy is forming way more stars than you would expect given its stellar mass. It has a star formation rate presently of something like 10 solar masses per year, compared to the Milky Way, which has like 1 solar mass per year. And the result of all of this star formation is that it is launching this superwind, which you can see here in the red. So this is all material that's being blown out of the disk of M82 by the starburst. So the combination of this supernovae that are going off and also some contribution from stellar winds. And I'll just note that M82 does not have an AGN. We have looked high and low for it, and we see no evidence of an AGN in this system. And so truly all of this material being expelled is due to stellar feedback alone. And the outflow in M82 is really impressive. So here I'm showing 2 scales. So here's a 10 kiloparsec scale bar here. Some other, outflows that you may have heard of. So going from AGN feedback on this side, where here I'm showing part of the Centaurus A jet and outflow. The Milky Way also has an outflow, the Fermi bubbles and the E Rosita bubbles. Whether it's AGN or stellar driven is, people argue about it. So I put it in the middle. And here you can see M82, which the disk of this galaxy is really small. But its outflow compared to its size is truly remarkable. And M82's outflow is really unique because it is so bright, you really can't miss it. It's obvious in any imaging that you do. And relative to its size, it's just enormous. These other outflows, for example, in NGC 253 that I'll talk about towards the end of the talk, and the Milky Way, you really have to try hard to see those outflows, but M82's is just very apparent. So these outflows from galaxies are inherently multi-phase. So they contain gas and material at a variety of temperatures and densities. The sort of cartoon schematic of this is that these outflows are biconical. But when they're starburst driven, they don't come to a point in the center of the galaxy like an AGN would, because they're being driven by this extended starburst. So it's a biconical outflow, but it has a flat bottom. The volume of this outflow bicone is filled with very hot gas that emits in the X-rays. And this is generally the fastest part of the outflow. And then along the edges of that cone is where the colder material can survive that doesn't just get, blasted away by the X-rays in the center of the outflow. And so this is where the colder, slower, ionized neutral gas, molecular gas, and dust typically is coming from, is the edges of this cone. And while the X-ray emitting phase is the fastest, it's actually the molecular phase that's quite slow and quite hard to detect that carries the bulk of the outflowing mass away from the galaxies. And these outflows are, of course, important in terms of galaxy evolution, because they can enrich the circumgalactic medium around the galaxies. They can quench star formation by removing material from the galaxy with which it could potentially have formed more stars. And if that material doesn't quite escape into the circumgalactic medium, it may rain back down onto the disk, providing new fuel to trigger more star formation in the future. So we had a cycle 1 JWST program to look at M82 and NGC 253, as I'll talk about in a few minutes. We were most interested in getting NIRCam and MIRI imaging of the entire outflow of M82. So with that, we had 6 bands of NIRCam tracing the 3.3 micron PAH feature, an H2 rotational line, an iron 2 line, which is a tracer of shocks, dust destruction, and as it turns out, supernova remnants, and 3 continuum filters that primarily trace the stellar light. In addition, we had 3 bands of MIRI imaging. We had 2 tracing the PAH features at 7.7 and 11.3 microns, and a continuum filter, again, tracing dust emission. So one complication of this is that JWST is an incredible instrument, and it's designed to detect, the furthest and faintest galaxies in the universe. But M82 is one of the brightest infrared sources in the entire sky. And so when you point JWST with all of its, immense sensitivity at M82, the center of M82 saturates the detectors immediately. There is no, you cannot have a integration time short enough to not saturate the detector. And so the strategy that we took was to use a subarray in the center of these galaxies to avoid saturating. The subarrays can be read out faster than the full array, and hence you can have a shorter, amount of exposure time that means you don't saturate immediately. And the reason why I'm talking about this at all is it's because this subarray NIRCam imaging of M82 was the first data that we got. And in fact, we got that data a full year ahead of the rest of our data and a year before we were expecting to get it. And so some of the first results I'm going to talk about are only using this teeny tiny subarray NIRCam imaging in the center of M82, which basically has like no exposure time because we just wanted it to be able to fill in the saturated center of the larger mosaic we were taking. So what exactly did JWST see when it looked at the center of M82? It saw the base of the superwind. So this is a gorgeous image that was produced for us by Alyssa Pagan here at Space Telescope for a press release that we had about a year ago. So if you're interested in reading that, you can scan the QR codes for either the NASA or ESA versions of this press release. In this image, you're seeing the disk of M82 sort of diagonally, and then these red filaments. This is the 3.3 micron PAH feature, tracing small dust grains. And this filamentary structure, sort of perpendicular to the disk, is real. That is the very base of the dust in this superwind at distances very close to the midplane. And so we are able to study the launching points of the superwind in relation to the starburst. So I've mentioned PAHs a couple of times, and I want to give just a super brief overview of them in case people aren't super familiar with them. So PAHs, or polycyclic aromatic hydrocarbons, are small dust grains or large molecules, depending on who you ask and which direction you're coming from. Here on the right, I'm showing an actual atomic force microscope image of a PAH that was synthesized in a lab. And so it's composed of these rings, these aromatic rings of hydrocarbons that make up this either large molecule or this very small building block of a dust grain. And PAHs are tracers of dust and the cold ISM. Rather than a sharp spectral line, they produce broad spectral features throughout the infrared due to this, complicated bond structure that they have. And although they are small, they are extremely bright. They can contribute up to 10% of a galaxy's total infrared emission. And in fact, they may contain a substantial fraction of the carbon in the universe, maybe locked up in PAHs. And JWST has really just transformed our ability to study the universe with these molecules, because we can now trace PAHs from, our own galaxy and our own solar neighborhood, in fact, all the way out to, cosmic dawn at redshift of 7 and everywhere in between. So they are an incredible tool that allows us to study the dust and cold ISM in galaxies across cosmic time. All right, so I showed you sort of the image of just the subarray in the center of M82, but since that time, we have now gotten our full mosaics with NIRCam and MIRI of M82. And so I want to show you what JWST saw over the full extent of the outflow in M82. So this is a gorgeous Hubble image of this galaxy with a scale bar showing 1 kiloparsec off of the midplane. And if we fade in our NIRCam image, so this is, again, the entire or most of the entire outflow of M82 seen with NIRCam, where the red here again is that 3.3 micron PAH feature. And so you can again see there are these filaments and bubbles and complicated structure in the outflow. And we also have data from MIRI, so at slightly longer wavelengths. And so here the green and blue are again showing PAH features, but that are larger than the 3.3 micron PAH feature. And again, here just the level of structure and detail is mind-blowing to me, that you clearly see these linear filaments coming off of the disk that then sort of devolve into this much messier network of filaments and bubbles and streamers away from the starburst. So we've had several papers come out of this group focusing on the outflow. And I'm going to talk briefly about the sort of main results from each of these over the next couple of minutes. So the first result that I want to talk about is that the way that we observe the 3.3 micron PAH feature with NIRCam is through a medium band filter. So here I'm showing a generic galaxy spectral energy distribution, where here is that 3.3 micron PAH feature. But this band pass shows the entire band of that filter that we use, and there's continuum below it that's due to the stars. And so if we want to see what the PAH itself is doing, we need to remove that stellar continuum out from underneath of it. And so the way that we did that in our setup is we bracketed this filter with 2 continuum bands on either side so that we can establish the slope of the stellar continuum and remove that from the F335M filter. It turns out it's not quite that straightforward because this PAH feature is really broad, and there's an aliphatic feature and a plateau that actually extend into this continuum filter next to it. And so we ended up using an iterative method developed by Karen Sandstrom to separate out the PAH contribution and the continuum contribution for this filter. And so with that method, we are able to take our observations of this F335M filter and separate it out into the stellar continuum and the actual 3.3 micron PAH feature. And so here you can see that the filamentary structure of the outflow really pops out once you get rid of the very bright starlight from the starburst core. So some more scientific results from this project. In a paper led by Deanne Fisher, she was looking at how these filaments in the PAH emission correlate with filaments seen at other wavelengths and in other phases. And so what she did was she took a slice across the outflow in the north and in the south, and those are shown in the thick black line. So that's the PAH emission sort of averaged in height across the outflow. And so these peaks that you see here are these sort of major filaments that you can sort of pick out by eye. And shown in blue in these figures is the X-ray emitting material from Chandra. And so sort of as expected in the north, where the X-rays peak, the PAHs are in a trough, and the PAHs peak sort of on the outside of where the X-rays are brightest. And again, this makes sense, right? The X-rays are sort of filling the volume of this outflow cone, and the PAHs are arising from the edges of that. And where there are a lot of X-rays, the PAHs are destroyed, and so they don't emit there. The southern side of M82's outflow is a mess, and it's known to be a mess for a long time. And so the fact that that trend is not as clear down here is not really surprising. The southern side of M82 is closer to M81, and so it's thought that that side of the galaxy in the outflow is being much more affected by this tidal interaction, as opposed to the north, which can kind of, sort of just canonically expand like it's supposed to. So that the PAHs avoid the X-ray emitting material is nice to see, but it's not super surprising. What was surprising is that when we look at the ionized gas traced here by Paschen alpha from Hubble, that's shown in red, there is an excellent correlation between the PAH emitting material and the Paschen alpha. And again, this is surprising because the 3.3 micron PAH feature that's being shown here is really small and really fragile. And so where there's a lot of ionized gas, you would expect it to be destroyed. And yet you can see in both the north and the south, excellent agreement between these two. The green curve in this plot and then the last ones is showing the CO data from NOEMA. So it's at significantly lower resolution. But you can also see that the CO follows these same trends, where the CO, the Paschen alpha, and the PAH emission are highly correlated with one another. So if we zoom in to this, rather than taking these big azimuthal cuts, if we look at how the PAHs are actually structured in the outflow, they're by no means homogeneous. So we are able to measure these sort of filament networks shown here in the white dotted outline. But within those, the PAHs are in these little clouds or cloudlets, where there are these discrete knots of PAH emission with some background connecting them. And this is in fact exactly what you would expect based on simulations of cold gas entrained in an outflow. It has this very clumpy structure that's not at all smooth. And so what we think is going on and why the CO, the PAHs, and the ionized gas are so highly correlated is because they are all coming from these clouds. If we had CO data at the resolution of JWST, the CO data would break apart into similarly small clumps and clouds. And so this emission is all coming from the same place. And in fact, as these clouds of molecular gas are immersed in this hot environment, the surfaces of those gas clouds become photoionized. And only the core, where it's sort of shielded from that emission, can remain molecular. And so the PAH emission that we are observing is arising from the photoionized surfaces of these neutral clouds. And so that is sort of what we think. There's such a great correlation between these three phases in the outflow of M82. So sort of building off of that, a postdoc, Vicente Villanueva, did a more detailed study of the correlation between the CO and the PAH clouds. And so what he found is by looking at the CO data, where the CO cloud catalog has already been compiled, and he extracted the PAH emission using the MIRI data in the same cloud regions. And so the PAHs with MIRI are slightly more robust than those in NIRCam. The molecules are bigger, and so they can survive a little bit more. And as you would expect, there is a very strong correlation between the CO brightness, shown here on the y-axis, and either one of the PAH feature brightnesses in these clouds. And so again, this is giving credence to the idea that the PAHs are coming from the photoionized surfaces of these molecular clouds that are being entrained in the outflow. What's surprising, though, is when you compare what's happening with M82, the symbols and the black dashed line, to this relation that's been derived for nearby regularly star-forming galaxies. So in the disks of regular star-forming galaxies, this trend between CO and the PAH intensity is almost 1-to-1. So they seem to be tracing each other equally well. However, in the outflow of M82, the CO is underluminous compared to the PAH emission. Again, it doesn't really depend on which PAH you use. And so this is signaling that in the outflow, the PAHs may actually be a better tracer of the cold material than the CO, because CO is being destroyed in the wind. And the idea here is that as your little cloud of molecular gas shrinks and shrinks away as it's destroyed by this hot environment, you're always going to have this photoionized surface where we think the PAHs are arising from. And you still have cold gas here. And so it might be that this PAH emission is a new way to trace cold material in the outflows of galaxies rather than relying on CO. And to sort of wrap up what is happening with the PAHs in the outflow, a graduate student at the University of Maryland, Serena Cronin, has been looking at which PAHs survive in the outflow. So my little cartoon to motivate this is that if you have a little tiny PAH grain shown here near the ionizing starburst, it will be destroyed by that harsh ionization environment before it makes it into very far into the outflow. It just gets ablated away because it's fragile and the starburst environment is very extreme. But if you have a larger PAH to start out with, it might get destroyed a little bit, but that grain is going to survive out to much larger distances. Moreover, in the starbursting center, those PAHs are going to be ionized, whereas as you move further away from the starburst, the PAHs will become more neutral. And so this is at least the expectation for what we should see. And by looking at these ratios of the 3 PAH features that we have from our NIRCam and MIRI imaging, Serena was able to confirm this, that as you move away from the starburst, you tend to be left with larger, more neutral PAHs, so more pinks and purples in this color map, and more sort of yellows and greens in this color map. And the only place that you really find these small grains is right near the starburst. They simply are destroyed and don't make it out very far. And so again, this is sort of in agreement with many theoretical models, but it's sort of nice to see it actually play out in the data itself. Okay, so I'm going to switch gears after this from talking about the outflow to talking about the starburst itself. But before I switch gears, I want to give you a quick pop quiz. One of these images is the Milky Way galactic center, and one of them is M82. So I want you in your head to think about which one you think is the Milky Way. They're both near infrared images, and I will fully admit that I am trying to trick you here. Okay, so if everyone has their guesses, the answer is the right one is the Milky Way galactic center seen with Spitzer. When I've done this in person, it's usually like a 50-50 split, and I've even tricked some Milky Way galactic center people, which feels really, really good. So the left image is M82 seen with JWST, and here's a much more fair comparison where the two are on the same physical scale. And so what's really exciting about this is that we are getting similar angular resolution to studies in the Milky Way, but M82 is 500 times further away. And so we can start doing Milky Way-like science in other galaxies, which to me is really exciting. All right, so going back to what JWST saw in the center of M82, this is a gorgeous image from the Hubble Space Telescope's NICMOS instrument at 1.6 microns. And when we compare it to what JWST saw at similar wavelengths, the difference is just astounding to me. Just the sheer amount of detail that you're able to see is truly revolutionary for how we study the stars and the star clusters in this starburst environment. And I just want to note that every single white dot that's in this image is a star or a star cluster. That's not noise, and we're not spatially resolving them, but there are stars everywhere throughout this galaxy. And what I'm going to focus on, and the analysis that I led, is of these big, bright, the kind of spatially resolved things. And these are the most massive star clusters in the center of M82. And so the punchline of this work that I led using our NIRCam data was that there's something like 1,300 massive star clusters in the central kiloparsec of M82. So these zoom-ins are showing just some selected regions of the galaxy, where the pink and blue circles are these massive star clusters that we have detected. By massive, I mean they have stellar masses greater than 10 to the 4 solar masses, assuming that they are a zero-age main sequence population. To put this number in a little bit more context, some of you may be familiar with 30 Doradus in the Large Magellanic Cloud. 30 Dor is the most extreme star-forming environment in the local universe, and it has a stellar mass of 10 to the 4 solar masses. And so M82 harbors more than 1,300 30 Doraduses in its central kiloparsec, and this is why it is a starburst galaxy. So in addition to uncovering just a mind-blowing number of massive star clusters in this galaxy, we were able to correlate them with previous massive cluster catalogs from HST. So now here on the right side of each of these zoom-ins, I'm showing the same region seen with HST, and the light blue big circles are those clusters identified in the HST catalog. And then the sort of darker blue circles are the JWST targets that overlap with that catalog, and the pink circles are JWST targets that are not seen in the HST catalog. And so the first result that we find from this comparison is that almost all of the clusters we find with NIRCam are new, meaning they are not seen in the HST catalog. And this is primarily illustrated through this bottom panel down here. It's simply that NIRCam sees through the dust better. This is a really dusty starburst galaxy seen edge on. And so just the longer wavelength of NIRCam enables us to see things that just simply are blocked by dust with HST. So here you can see that most of these pink circles are just totally absent of any emission in the HST data. The other sort of at first confusing result that we had is that we only detect half of the clusters that are in the HST catalog, which is confusing because if a cluster has optical emission, it should also have near-infrared emission. And the reason for this is not that those clusters aren't there. It's that the resolution of NIRCam means that things that were monolithic large structures in the HST catalog break apart and now fall below our mass criterion for being a massive cluster. And so you can see in this panel, there are a ton of light blue circles highlighting a very dense cluster environment as seen with HST. And when we go to JWST, it's not that there isn't stellar emission there. It's that all of these big things break apart into much smaller objects that no longer look like clusters and no longer meet our mass criterion. So another result from the work that I led was that even though the near-infrared allows us to see through the dust better, we are not free from dust's effects. So here I'm going to plot a color-color diagram. So if you're not familiar with color-color diagrams, things to the right and up are redder, and things to the left and down are bluer. So here I'm plotting all of those 1,300 star clusters in M82. The contours are density to help guide your eyes. And the first thing that you can see is that this population of clusters is offset from 0, 0. So already you can tell that these clusters are reddened, likely due to dust. To sort of make that point even more apparent, this red curve here with the numbers above it is a dust-free single stellar population model at different ages. And so this is how a cluster with no dust would evolve through this diagram as a function of age. Now, we don't have great age estimates or really age estimates at all for these clusters yet. We are hoping to get that soon. But sort of regardless of which age you pick, these are clearly above and to the right of this prediction, which means there must be dust in these clusters. And in fact, there's something like 3 to 24 visual magnitudes of dust in these clusters, even still in the near infrared. And so when we go to analyze our MIRI data that we have, we expect to find more embedded star clusters than we're able to see in the near infrared. So in the last few minutes, I want to quickly switch gears to another galaxy. So this is the galaxy NGC 253, shown here on the right. This is another prototypical starburst galaxy in the local universe. It's at almost the same distance away from us as M82, but NGC 253 is a Milky Way mass galaxy. So it's seen edge on, it has a bar, and it's not really interacting with anything. It has a couple of little dwarf galaxies, but it's not undergoing a major tidal interaction like our friend M82 is. And so in this same JWST program that I've been talking about, we also targeted NGC 253 with the same sort of MIRI and NIRCam setup as we had before. But what I want to talk about towards the end here is that we also got spectroscopy in both galaxies. So we have MIRI medium resolution spectroscopy targeting the region over the superstar clusters. So the center of NGC 253 is governed by its bar. So here, zooming in to some of our JWST MIRI data in this galaxy, the bar is sort of governing everything that happens in its center. And the starburst in 253 is concentrated in a much smaller region of space that's only a couple hundred parsecs across. So if we zoom into the very center of this galaxy, and we use ALMA to look at the densest, youngest collections of gas and dust, this is what is revealed to us. So this is ALMA data looking at the dust continuum emission, so that you're looking at emission from warm dust in the center of this galaxy at a resolution of better than half a parsec. And these are the sites of these so-called superstar clusters. So these are the youngest, most highly embedded star clusters in the center of NGC 253. And they are still incredibly gas-rich, and they are still growing and forming. Now, at first, it seems kind of weird that this structure is very linear. The linear structure is because this galaxy is edge-on. And as I'll show in a moment, it's actually that these clusters are in a ring that you're seeing edge-on. So bars funnel material down to the centers of galaxies, and they act sort of like a gas highway. So there are a family of orbits that's set up by the bar called the X1 orbits. And it's along these orbits that gases move from large radii down to smaller radii. So sort of like a highway going into a major city is very good at taking cars and people from further out from the city down to closer to the city center. At smaller radii, there are another family of orbits called the X2 orbits, which are perpendicular to the bar. And these help funnel material very close down to the center of the galaxy. And so you would expect that at the innermost X2 orbit, there will be a pileup of material. So similarly, like if you've ever driven into a major city at the same time as a bunch of other people for maybe a sporting event, once all of those people get off of the highway and are now in the city center, there is a traffic jam because there's all of this material and kind of nowhere else for them to go. And something similar happens in the centers of galaxies, where all of this material is flowing in along the bar, and then it gets to the innermost X2 orbit, and it kind of runs out of places to go, and so it piles up. And when gas piles up, it collapses more efficiently, and it forms stars as massive clusters. And so we indeed see that in the center of NGC 253, the massive star clusters and the youngest star clusters that we detect with ALMA lie pretty much exactly where this innermost X2 orbit is, just like we would expect from this theory. And in fact, we were able to show that kinematically, the clusters are in a circumnuclear ring that bears striking resemblances to the center of our own galaxy, the Milky Way. So here, to scale, is sort of a top-down, deprojected view of the central molecular zone of the Milky Way and the central molecular zone of NGC 253. Now, in the last minute here, I want to show some of the MIRI MRS spectroscopy results that I'm currently working on. So these are preliminary. And for that, I want to focus on one cluster in particular, this one up here, superstar cluster 14, which is the most massive cluster in the starburst, as a stellar mass of 10 to the 5.5, a gas mass of about the same, and its radius is only half a parsec. And we know from our ALMA data that there's an outflow emanating from this cluster that's roughly spherical, and it's the combined effects of all of the stellar winds and radiation pressure from all of the massive stars lurking in this cluster that are driving this massive outflow of material from it. And this may indicate a gas clearing phase in this cluster's evolution. So with our MIRI MRS data, we were able to extract the full mid-infrared spectrum of cluster 14. So that's shown here in this black curve. And you can see that we detect a bunch of spectral lines. And in fact, here are the line profiles of some of those lines. And for many of them, especially the ones tracing the ionized gas, so all the ones here in blue, they very strongly favor a two-component fit. And it is this sort of broad blue shifted component that you see in these fits that's indicating that we are detecting an ionized gas outflow from this cluster, which is super exciting and expected given that we know there's a molecular gas outflow. But it's nice to see the other more prominent phase of this outflow in so many tracers. So stay tuned for more updates on this project, which again is in its very early stages. And so in the interest of time, I hope that I have I've given you a whirlwind tour through what we're learning about M82 and NGC 253 with our JWST data. And I will just leave my conclusions up on the slide, and I am more than happy to take questions from people. Thank you.
Thank you very much, Rebecca. Amazing talk, very interesting results. Thank you. So we have time for questions. You can raise your hand. The question if you want. Armando?
Hello, can you hear me?
Yes.
Okay, thank you, Rebecca. Thank you for the very nice talk and all the hard work to put all this data together, which I can only imagine it was really tough for you. I have a few questions. One of them is when you were discussing that only the PAHs, the large PAHs, were surviving all the way to the top of the wing. Is that because it takes time for them to travel, or is because the change in temperature of the gas inside the hot phase, or maybe also the change in the intensity of the X-ray background?
So it's primarily that the small dust grains get destroyed before they can really get started. So they are destroyed, the smallest ones get destroyed very close to the ionizing starburst and simply never really make it into the outflow very far. Of course, we do see them, in those beautiful images I was showing, but they are much less likely to survive even getting out of the starburst because of the radiation environment there. And then as they move out, they may continue to shrink again as they're bathed in this X-ray background. So sort of a combination of a couple of things.
Yeah, but probably after a little bit, once that the temperature drops, the ones that did it, the ones that survived probably will have a much easier work to be done afterwards. And the other thing I had, if I ask too much, too many questions, Enrica, please stop me.
No, don't
The other thing is, you said that all the individual sources that we see are actually clusters, not really individual stars, because you mentioned that we don't resolve them. So, but not even, for example, AGB stars, you will expect to see, especially at those wavelengths, especially in the halo. I mean.
Yes, yeah, sorry if I misspoke. Yeah, so every single white dot in this image is either a star or a star cluster. And so we are certainly seeing some individual stars. AGB stars are really bright in the near infrared. And we're also likely seeing, individual OB associations. Unlike, in like the local group, we see these, we see evidence of these stars, but they're point sources. We can't, detect, we can't do like resolved stellar population stuff with this quite yet. These larger things, those are definitely clusters of stars. And when I compiled my cluster catalog, one of the criterion that I used was to remove AGB stars specifically. So there was basically a concentration index cut that we did. Anything that was 2-point source like we threw away, because in the infrared, AGB stars can have the same luminosity as a star cluster. And we wanted to really have a clean catalog of things that were definitely only star clusters.
You also have probably like a smaller, I mean, so there might be more star clusters that actually are so compact that it could be, have been excluded because they could also be AGB stars.
Yes, exactly. It is possible that we are missing some smaller clusters, but we wanted to make sure that we got rid of everything that was not a cluster. I'll also, while I'm here, briefly just note that this number of clusters depends on the age that we assume for the star cluster, which we don't have yet. And so if instead we use a slightly older age, so the HST cluster catalog assumed an age of 8 million years, this number is roughly halved, but that's still certainly a lot of star clusters or potential star clusters, sort of regardless of which age you pick.
My last question, I promise. When you estimated the dust attenuation, do you think that's mostly due to a screen foreground extinction, or basically because you are measuring through the line of sight of the disk, or could be internally mostly?
Both. So certainly foreground extinction is a huge problem for us. Again, you're looking through an edge-on disk. Both of the galaxies I talked about are edge-on, and so this is a problem for both of them. But at least for the youngest clusters, their environment is still dusty as well. And so it's likely that in this case, it's mostly foreground dust, but certainly some of these will have dust envelopes around them still. And when we go to MIRI, we expect to see more of those that have, dust in their local environment.
Thanks a lot, Rebecca. Thank you.
Any other questions? I have a curiosity. I was wondering if do you have any plan to observe your star cluster in, for example, with a VLA or SMA facilities? Yeah,
so for M82, there is SMA data that we are working on publishing. So M82 is very far north. It's at like plus 70 degrees. And so you can't point ALMA at it, unfortunately. And so we do have SMA data of M82 in the most extended configuration. And there we do see, knots of dense molecular gas like we see in NGC 253. The physical resolution is much worse, unfortunately. And so we're not looking at individual clusters. We're sort of looking at, giant molecular cloud-ish scales. But we do see, candidate, cluster locations in those data. For the VLA, there's certainly VLA data on both of these galaxies that exist. The highest resolution, I think that highest physical resolution that we have is just about 2 parsecs for NGC 253. And that's sort of as good as we can do with the current VLA. The next generation very large array will be transformative for the studies of star clusters, both in these galaxies and out to slightly more distant systems as well.
And are you planning to analyze, to apply the same analysis to other kind of galaxy like AGN, starburst, composite galaxy, like, I don't know, NGC 4945?
Yes, we love NGC 4945 in this group. So we have been applying for JWST data on that galaxy, and unfortunately it hasn't gone through because it's incredibly competitive. I have some ALMA data on a LIRG, so luminous infrared galaxy, VV114. So it was part of the GOALS early release science program with JWST. So it has a ton of JWST data. And I have a program to get the molecular gas component of it to try to find the embedded clusters in that galaxy and to do, a very similar game of where are all of the clusters in this galaxy, and what is the feedback looking like in that much more complicated system that's merging and has an AGN and has star clusters all over the place.
Okay, thank you. And my last question, I think, I was wondering, I don't know if in simulation, you mentioned that you compare your data with some kind of simulation. I don't know exactly what kind of simulation you refer to, but I was wondering if, what is the role of the magnetic field in confining the PAHs within the outflow galaxies?
Yeah, so that is a great question. I don't think we know the answer to that yet, but there are simulators in our group. So specifically Evan Schneider's group, and she has a grad student working on this right now, who are using these hydrodynamic simulations that include feedback and magnetic fields to exactly learn what the magnetic field is doing and how it's shaping, the structure of the outflow. So in progress.
Okay, thank you. So any other questions? Well, if not, let's thank Rebecca again. Thank you very much, Rebecca.
Thank you. Thank you so much for having me.
And thank you very much to all for joining us. Well, thank you.
Have a good day. Everyone. Bye.
Have a good day. Bye. Bye. Thank you, Rebecca.
Thank you.